Hello children, in this video we are going to talk about extraction of metals from their ores. So what is an ore? A naturally occurring solid raw form of a mineral is called ore, right? Then the ore, because it is occurring naturally in the earth's crust, it has impurities like soil or sand. By default, they are mixed into the ore. So there are three steps that are involved in the extraction of metals from their ores. The first step is called enrichment of the ore, where we remove the gangue, that is the impurities like soil or dust or sand, whatever is present in the ore. It could be done through different ways like washing with water or any other ways. Just that the gangue is removed from the ore, so this is the enrichment process. The second step is reduction of this ore. Now metals, they exist in their combined form, that is they exist in the form of their sulfides or chlorides or oxides or maybe even carbonates. So they are reduced to pure metals by using different processes. This process is called reduction. The third step is electrolytic refining. Now once these metals are reduced in the second step, they are still they still have certain impurities. And the third step is to electrolytically refine these elements so that these impurities also get away and we get purest form of these metals. Now let's look at different categories in the reactivity series. There are different ways for metals that are lower in the reactivity series. For example, mercury and copper. These metals are placed lower in the reactivity series and they are just found in their sulfide forms, which can be reduced only by heating in the presence of oxygen. When we heat these metals, the ores of these metals in presence of oxygen, the oxygen combines with sulfur, liberating sulfur dioxide, and the metal gets separated. So it is a very easy process for metals that are lower in the reactivity series. Now let's look at metals that are in the middle of the reactivity series, that is zinc and iron. So if you look at zinc, zinc exists as zinc sulfide also. Zinc also exists as zinc carbonate. So when a sulfide ore is existing, then it is converted to its oxide form by heating it strongly in the presence of excess of air. And this process is called roasting. The carbonate ores, they are heated in limited amount of air to get the oxide form of the ore. This process is called calcination. So what is the difference between roasting and calcination? Basically, roasting is done for sulfide ores, calcination is done for carbonate ores. In roasting, excess of air is used, and in calcination, limited amount of air supply is there. Both these processes give the same product, that is the oxide form of the ore. So the sulfide and carbonates are removed and we get the oxide form of ore. In case of zinc, we get zinc oxide at the end of the roasting or the calcination process. Now once we have the oxide form of the ore, they are reduced using carbon. What do you mean by reduction? We've already done that. Reduction means removal of oxygen. So from the oxide form of these ores, this oxygen has to be separated to get the metal, right? So that reduction is done using carbon usually, but there are certain cases where this reduction can also be done using metals that are higher up in the reactivity series. For example, aluminium is a very common reducing agent, so it can be reduced, it can be used to reduce manganese oxide or even to reduce iron oxide. Now, whatever way reduction is being done, it is a highly exothermic reaction when a metal is reduced to its pure form. So how do we use, what do we do with the heat that is liberated in this process? When iron oxide is reduced using aluminium, which is a highly reactive metal, we get iron and aluminum oxide and a lot of heat is liberated. This heat is even used to join the railway tracks, and this process is called Thermite reaction. So here it is very important to remember what is Thermite reaction. When iron oxide is reduced using aluminium, it is a highly exothermic reaction liberating a lot of heat which is used to join the railway tracks. So this is called Thermite reaction. So we have done the reduction of metals that are in the middle of the reactivity series. Right? So just to repeat, these metals, the ores of these metals, they are usually in the sulfide or carbonate forms. They are first converted to their oxides, and then the oxides are reduced using either carbon or a more reactive metal. Right? Now coming to metals that are higher in the reactivity series. Now, because they are already so high up in the reactivity series, they are highly reactive. These metals have high affinity for oxygen, so they cannot be reduced by carbon. They exist in the form of chlorides and oxides, but they cannot be reduced by carbon or by even high reactive metal, because there is no metal that is more reactive than these. They are already at the top of the reactivity series. So how do we reduce them? So for such metals, if you look at sodium, calcium and magnesium, they exist in the form of their chlorides, and they are reduced by electrolytic reduction. Now what happens in electrolytic reduction is their solution is basically used as an electrolyte, for example sodium chloride, and when electricity is passed through that electrolyte, sodium gets deposited at the cathode. Cathode is the negative terminal. So metals, they are positively charged ions. So these positively charged ions get attracted towards the cathode and get deposited at the cathode. Now the negatively charged ion, that is the chlorine ions, they get deposited at the anode. So in these three cases, you need to remember sodium, calcium, magnesium, chlorine gas is liberated at the anode. But if you look at aluminium, it exists in the form of bauxite, which is basically aluminium oxide. Now when that is reduced using electrolytic reduction, we get aluminium at the cathode and oxygen gas is liberated here at the anode in place of chlorine, because it was in the oxide form. So this is how metals are reduced that are high up in the reactivity series. So we have just gone through the second step, major step of purifying, that is reduction. Now what is electrolytic refining and why do we need this now? We have already extracted the metals from their combined forms, chlorides, sulfides, oxides, carbonates, whatever. We got the metal. The metals that are at the top of the reactivity series, they have been reduced by electrolytic reduction, so they do not need any further refining. But the metals that were in the middle or the bottom of the reactivity series, we have reduced them using different processes like reduction with carbon or maybe just by heating with oxygen. So what happens is the metals that we get after reduction process, they still have certain impurities. So these impurities are removed using electrolytic reduction. So basically electrolytic refining, sorry. So this electrolytic refining is done for metals that are in the middle of the reactivity series or at the bottom of the reactivity series. So how it is done? A thin strip of the pure metal, whichever metal is being refined here, is made the cathode, and a solution of that metal is made the electrolyte. For example, if we pick up copper, copper sulfate is used as electrolyte. Again, it is acidified copper sulfate. Why acidified? So that the solution becomes more conducting. That is the only purpose of adding acid to an electrolyte whenever we do electrolytic refining or electrolytic reduction processes, right? And the anode is basically the impure or maybe the metallic form that we have just obtained after the reduction process. So what happens is from the anode, the ions of the metal, they get dissolved and they get into the electrolyte, and from the electrolyte, these ions get deposited at the cathode. So basically at the cathode, we have the pure form of metal getting deposited, and whatever impurities were there at the anode, they settle down in the form of anode mud. Right? So this electrolytic refining is done only for metals that are in the middle of the reactivity series or lower in the reactivity series, but not for metals that are high up in the reactivity series. They have only two steps, that is enrichment and reduction, because their reduction has been done electrolytically, so they don't need further refining. Electrolytic refining is needed only for metals like zinc, iron, copper and mercury. So I hope this helps you to prepare extraction of metals from their ores. Okay, thank you.